So this is the fourth lesson in probability, and in this lesson we are going to look at the tree diagram. It happens that this is one of the areas in probability that I enjoy and you may also enjoy, because it deals with the mutually exclusive events and independent event at the same time. So what is a tree diagram? A tree diagram, just like the word suggests, is like a tree growing branches horizontally, which is a method that we use to be able to analyze events in probability, and then we are able to get probabilities from the branches formed by the tree. Maybe you understand this once we do an example or few examples. You'll be able to see how easy it is to work with the tree diagram. So let's have an example to see how the tree diagrams work. So this is our example 1. If a coin is thrown 3 times, the tree diagram would look like this. So the tree diagram, if we toss a coin 3 times, we start with the first branch. So that is our first branch. You can put 0 here as a starting point, or it's not all that necessary. So we say, if you toss a coin the first time, you can get a head, or you can get a tail. If you toss the coin again, if you got a head in the first toss, then you can have, the second time you can have a head and you can have a tail. That is the first branch. We come to the second branch. If you toss the coin the first time you got a tail, then you can toss it the second time. You can either get a head or you get a tail. You toss it the third time. So first time you can get a tail, second time you can get a tail, the third time you can get either a head or you can get a tail. That is the last branch. The other branch, you can toss the first time you get a tail, the second time you get a head, the third time you toss, you can either get a head or you can get a tail. So we are through with that branch. We come to this other branch. You can toss the first time you get a head, second time you get a tail, the third time you can toss, you can get a tail or a head. Then this upper one, you can toss the first time you get a head, second time you get a head, the third time you get a head or a tail. So this is what we call the tree diagram. Then you can feel the probability. When you toss a coin, the probability of getting a head is a half. The probability of getting a tail is a half. Then the same case appears here, 2, a half, a half. Here it is a half, it is a half. Here it is a half. The probability of getting a tail is a half there, a half there. We have a half there, we have a half there, we have a half and a half. So those are the probabilities that you would feel. Then in my introduction I said that in this case we deal with the mutually exclusive as independent event. So when you toss a coin the first time, you get a head or a tail. These are mutually exclusive event, because when you toss a coin the first time, you either get a tail or a head. If you get a head, you can't get a tail. So those are mutually exclusive. When you toss the second time, you can get a head. So by getting the head the first time does not prevent you from getting the head the second time. So that is an independent event. We can analyze our probabilities here, that in this case, if we follow this branch, we get a head, and a head. Then if you follow this branch here, I follow this one, you follow that, you get a head, and a tail. Then you can follow the other one. This a head, a tail, and a head. So it's a head, a tail, and a head. So that is that branch. This one is a head, tail, tail. So this is a head, tail, and tail. We are through with that branch. We come to the second branch. This is a tail, head, head. So it's a tail, head, head. The other one is a tail, head, tail. This other one is tail, tail, head, tail, tail, head. And finally we have tail, tail, tail. So these are the outcomes that we get from the tree diagram, and they are mixed of mutually exclusive events and independent events. So the reason why I'm saying it is very easy to work with the tree diagrams, and you can actually solve most of the probability question using the tree diagram, is that you can be able to see all the outcomes here. For example, if you are asked to find the probability of getting a head, two heads and a tail, you can come and check two heads. Here we have two heads and a tail, so we can say that is 1. Here we have one head, so that is not possible. Here it doesn't qualify. Here we have two heads and a tail. Here we have one head. So it's only two, and this one, two heads and a tail. So we can say we have 3 outcomes where we have two heads and a tail out of 1, 2, 3, 4, 5, 6, 7, 8 out of 8. So the probability of getting two heads and a tail is equals to 3/8. The probability of getting one tail, that is a tail, and two heads, and that seems to be the same, so let's change that. The probability of getting 3 tails is equals to, we have only one occasion where we have 3 tails, this one, so it is equals to 1/8. So that's why I'm saying working with the tree diagram in probability it's not only easy but very interesting, and you are sure if you do your probability. Then here you can also use the probabilities that we have indicated. For example, just to show you that the tree diagram is a mix of mutually exclusive and independent event, let's take the first point. We said that the probability of getting two heads and a tail. So it is equals to, the first branch we identified is this one. So it can say this is equals to probability of getting a head and a tail. So this branch here, a head and a tail. We are through with that one. The other one is this one, where you get a head, a tail, and a head. So here, so those are independent event. And alternative, or the probability of getting a head, a tail, and a head. So there we have and. Those are also independent event. Or the probability of getting, the other one is tail, head. This one here. So we say probability of getting a tail and a head, not a tail but a head, and a head and a head. So those are the probability. Then we can now work out on probability. When you separate this is a half multiplied by a half multiplied by a half. or plus, so this is a half multiplied by a half multiplied by a half. The probabilities that we have indicated here, this probability, plus, can put the brackets there, a half times a half times a half. So you can see this is a mixture of independent event and mutually exclusive event. So it is 1 over 8 plus 1 over 8 plus 1 over 8, and you get 3 over 8, which we have obtained here. So you can either use the outcomes or you can use the probabilities that are indicated in the tree diagram. So let's have a look at now another example. So here is another question. We are told in a certain village 10% of the people are bold-handed. If 4 people are chosen at random, find the probability 3 are bold-headed, less than 3 are bold-headed, 3 are not bold-headed, at least 2 are bold-headed. So for you to be able to do this, what we do, we have said in our earlier lessons that you can use percentage, fraction, or decimals to represent probability. So here we are using percentage, and we know 10%. 10% is the same as 1 over 10 in terms of fraction, 1 over 10 or 0.1. So we can use either. We also use the tree diagram to do this. So let's first of all draw our tree diagram. We start from here. We are going to use B to imply bold-handed, and B with an apostrophe to imply not bold-handed. So you can choose the first time, you get a bold-headed person. So you choose the second time, you can get a bold-headed, or you can get a person who is not bold-headed. You move to the other branch, we have, you can have, first time you have bold-headed, second time you have bold-headed, or you can have somebody who is not bold-headed. So that is the second one. Then we move to the third choice. So here we can have bold-handed or not bold-handed. We have this one, the third choice. We can have bold-handed or not bold-handed. Then we have the third choice in the other branch. You can have a person who is not bold-headed, a bold-headed, and then we are bold-headed or unbold-headed. Then this other one, you can have a bold-headed or not a bold-headed. That is the third choice. The fourth choice, we have a bold-headed or not a bold-headed. Then this one, you have a bold-headed or not a bold-headed. This one we have to squeeze here. So we have a bold-headed and not a bold-headed. This other one, we have a bold-headed or not a bold-headed. Then we have this one, we have a bold-headed or not a bold-headed. Then we have a bold-headed or not a bold-headed. We have this other one, we have a bold-headed or not a bold-headed. And lastly, we have a bold-headed or not a bold-headed. So these are the 4 choices that we have been told that the 4 people are chosen at random. From there, what remains now is to fill also the probabilities. Since we are saying 10% of the people are bold-headed, it means this is 1 over 10 bold-headed and 9 out of 10, which also represent 90. So this is also 1 over 10, This is 9 over 10. This is 1 over 9. 9 over 10. This is 1 over 10. 9 over 10. So you can fill the whole tree diagram with the percentage. So this is 1 over 10, and this is 9 over 10, 1 over 10, 9 over 10, 1 over 10, 9 over 10, like that. But we know the probabilities. Now what remains is to now calculate the probabilities that we have been asked out of these outcomes. So before we do the calculation, maybe we should write our outcomes. So the first branch we have, this one is B, bold-headed, everybody is bold-headed. The other branch is this one. It is bold-headed, and not bold-headed. So it is B, and not bold-headed. The other option is this one, which is B, not bold-headed, bold-headed. Then we have this one, which is bold-headed, not bold-headed, not bold-headed. Then we have this one, which is bold-headed, not bold-headed, bold-headed. Then we have this other option, which is bold-headed, not bold-headed. So bold-headed, not bold-headed, bold-headed, not bold-headed. Then we have this other one, which is bold-headed, not bold-headed, not bold-headed, bold-headed. Then we have this one, which is bold-headed, not bold-headed, not bold-headed, not bold-headed. We are through with that. Then the second choice is this one. We have not bold-headed, bold-headed. Then we have this one, which is not bold-headed, bold-headed. Then we have bold-headed. Then we have not that one. So this other one is not bold-headed, bold-headed. So the third one is bold-headed, not bold-headed. Then we are here, which is not bold-headed. We have bold-headed. Then we have not bold-headed. Then we have bold-headed. Then this other one, we have not bold-headed. We have bold-headed, not bold-headed, and not bold-headed. Then we have this other one. We have not bold-headed. We have here we have not bold-headed, bold-headed. That's not correct. So this is bold-headed. Then we have this one, another one. It is not bold-headed, not bold-headed. Then we have bold-headed and not bold-headed. Then this other one, it is bold-headed, not bold-headed, and finally bold-headed. And we have the last one, which is bold-headed, not bold-headed, not bold-headed, not bold-headed, not bold-headed. So those are the outcomes that you get from our tree diagram. So our first probability, at least we are three are bold-headed. So let's have a look at how many options do they have where we have 3 are both-handed. So the probability that 3 are both-handed, we have that option. That is one option. 3 are both-handed. This is also another option. This is also another option. This is not, this is not, this is not, and this is another option. So probability that the 3 are both-handed is equals to, we have 4 options, and the total is, we have 16 outcomes. So 16 outcomes, this is equals to 1/4 when you simplify. So that is the probability that the 3 are both-handed. You can also use the probabilities of maybe 1/10 and 9/10. They should give you the same result. But this is simpler because we are dealing with outcomes. The other part B, less than 3 are both-handed. So let's have a look at so less than 3 are both-handed. So the first option, we have all are both-handed. The second one, 3 are both-handed. The third one, so this is one of them. Less than 3 are both-handed. This other one does not qualify. This is there. That is there. Less than 3 are both-handed. So we have this one. 2 are both-handed. So they are less than 3. Here we have also 2. Here we have 1. Here we have that. It is quite less than 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So probability, that is part B, probability that less than 3 are both-handed is equals to 10/16, which when you simplify it is 5/8. So that is 5/8. Less than 3 are both-handed. Then part C, we are going to look at the probability. There are not 3 are not both-handed. 3 are not both-handed. So that is 1. 3 are not both-handed. That is 3, 2. This is 3. This is 4. And 3. And that is, so we have the probability 3 are not both-handed. We have 3 are not both-handed, so we can say it is B prime. It is equals to, we have 1, 2, 3, 4, 5, so it is 5/16. And we have part D, we have at least 2 are both-handed. So at least 2, we start with the first one, that is 4 are both, at least 2. So that one qualifies. So we have 1, at least 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have at least 2 probability. At least 2 are both-handed. We have said it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I can find 11, so it is 11/16. At least 2 are not both-handed. So that's how we work with the tree diagram, and you can see it simplifies the work, because for you to determine this probability without the tree diagram, is a bit complex. So let's have a look at another example. So here is our example 2. In a volleyball tournament, two teams A and B are playing. The rule to determine the winner is the first team to win 2 consecutive games or a total of 3 games. Draw a tree diagram to represent this information. So let's start with from the beginning. So we say that is our starting point. So you can say A can win the first game or B can win the second game. If A wins the first game, they play another game. A can win the second game or B can win. Now it means, since we are saying the rule of is that the first team to win 2 consecutive games, it means that A will have won the tournament at that stage. We come to the second option. A can win the first game, B can win the first game, and the second game A wins or B wins. If B wins the second game, it means it won because it has won 2 consecutive games. But if A wins the second game, they have to play the third one. If A wins the second game, then it means that A has won 2 consecutive games, so it has won. If B wins the third game, it means they have to none of the team has won 2 consecutive games or 3 games in total. So it means they have to play another one. And if A wins that game, then it means A can win or B can win. If B wins, then it means they have won a total of 3 games, and then that means it will be the end of the game. So that is how you represent that information on a tree diagram. So we can say here A has won 2 consecutive games. Here there is no win. A here has won because B won the first game, A won the second, A won the second. So they have won 2 consecutive games. In this case, we don't have a winner. A loses because B wins the 3 games. So in this case, B wins the first one, A wins the second one, B wins the third and the fourth. So B has won 3 games out of the 4, and in this case, B has won the first one, B has won the second one. So that is how you represent that information in a tree diagram, and you can be able say that's a question, but now you can calculate the probability of the team winning. So you not go further, but once you draw the tree diagram, you should be able to calculate the probability. So let's have a look at another example. So our example 2, we are told in a volleyball tournament, 2 teams A and B are playing. The rule to determine the winner is the first team to win 2 consecutive games or total of 3 games. Draw a tree diagram to represent this information. If any one game, the probability that either team wins is a half. Find the probability that tournament end after only 2 games. B, 4 games need to be played to determine the winner. C, team A wins. So let's first of all represent our information on a tree diagram. So that is our starting point. So team A can win the first game or team B. Then the second game, if A wins the second game, it means it has won because it has satisfied 2 consecutive games. Alternatively, B can win the second game, meaning they have to play another one. Higher. We come to the other branch. A can win the second game, so it means they have to play another one. If B wins the second game, then it's first and second, then it means it has won. We come to this branch. If A wins the first game, B wins the second, then we have A winning the third, B winning the third game. It means B has won because it has won 2 consecutive games. The A won the first one, but B won the second and the third. Alternatively, in our other branch, if B wins the first game, A wins the second game, then it means the third game A can win. If A wins, then it has won the tournament because it has won two games. If B wins, then it means that the game has to continue. Now, if B wins the third one, then if A wins the third, our B wins the fourth tournament, then it means B has won because it has won 3 games out of 4. Then this one, if A wins, then it means it has won the tournament and B can win. So this means that this is the farthest we can go for the tournament to end. This is where we have A winning. If B, then we don't have a winner, A will win. So that is how you represent that information on a tree diagram. Then after that, we have the probabilities. Let's fill the probabilities. So we are told the probability of any one team winning is a half. So this is a half, this is a half, this is a half, a half, a half, a half. We have a half, a half, then we have a half here, a half here. Here we have a half, here we have a half, here we have a half, and a half. So those are the probability. So find the probability. We start with part A. Find the probability that tournaments end after only 2 games. So the probability 2 games end after only 2 games is equals to, it is either we have probability of A winning and A winning. This is the first option we have here. Or we can have the probability of B winning, this part here, B winning and B winning. So the probability of A winning, here we can write probability of A multiplied by probability of A plus probability of B multiplied by probability of B. That is why I mentioned that in tree diagram we can combine both mutually exclusive and independent events. So this is a half multiplied by a half plus a half multiplied by a half, and this is a quarter plus a quarter, which is equals to a half. You get a half when you add a quarter and a quarter. So that is a probability that the game ends after only 2 games. Let's go to part B. So 4 games need to be played to determine the winner. So we have part B. 4 games. This is we can have A winning, B winning, A winning, then A winning. So these are four games, and also B can win, A can win, B. So those are the occasions or outcomes where 4 games need to be played to determine the winner. So we say the probability of 4 games to be played to determine the winner is a probability that we have A winning and B and A and A, or probability that B wins, then we have and A, and we have A and B, and finally we have B. So those are 4 outcomes, the outcomes where we need to have 4 games played to determine the winner. So we can separate this and say this is a half multiplied by a half multiplied by a half multiplied by a half. So that is the first one. Then we have plus, we have plus, the other one is, we can put a half multiplied by a half multiplied by a half multiplied by a half. So when you compute that, this will give you this is 1/8 plus that is 2 times 4, this is 1/16, not 8. Plus 1/16, which is 1/8 when you add. So that is the probability that 4 games need to be played to determine the winner. So finally, team A wins. So let's use this space here. See, team A can win 3 times. So if it wins 2 consecutive games, that is okay. It can win 3 games out of 4, that's another win, and it can win 2 consecutive games after B wins the first one. So these are the probability where A can win. So we can say probability A wins is equals to probability of A and A winning, that's the first option, or probability that we have A, we have B, we have A and A, 4 games, or we can have the probability. The other probability is if B wins the first game, then A, and finally, or we can say probability that those are 3 I think we are okay with that. Those are the 3 probabilities where A can win. Therefore, we now compute our probability, which is a half times a half plus a half times a half times a half times a half, or a half times a half times a half, which will give you, when you compute, you should get 7/16. And that brings us to the end of our lesson. Hope you have enjoyed. You can look for questions from past papers and KCSE papers, and you should be able to work them out. So after this, you can watch the whole topic, or you can watch individual lessons. So thank you for watching.